Hello everybody! I hope everybody's having a wonderful day. So today we're going to be talking about complexity analysis. So the big question really that we're going to be talking about today is ultimately really this. So what are some desirable characteristics for algorithms so that we can compare them? So that's going to be kind of the big question of this lecture. In particular, I'm going to talk about how we really could say, okay, well, if I give you two algorithms, how do I stack up and say this algorithm is kind of better, it's better than this one in a more mathematically rigorous way? So before we get into more of that kind of deeper way of thinking about things, I want to kind of keep it top level here and think about what are some desirable characteristics an algorithm can have. Now, I want you to think about this with me, and I'm going to kind of rattle off some ideas. And all of these seem perfectly valid ways of thinking about what would be some desirable characteristics so we can compare them. So one that might be one that you might think of would be conceptual simplicity. So this is one idea I think might work pretty well. Sometimes when you describe an algorithm, the ideas for which the algorithm is described, if they can be very simple and easy to communicate, that's wonderful. Some algorithms, even if they aren't necessarily the fastest, sometimes are the easiest to communicate. That's one idea, maybe. How about, let's think about something more practical. Beyond that, how about the difficulty to implement? So that's maybe one to think about. If I give you an algorithm, it might naturally be, okay, well, how easy is this to implement on a computer? So putting in my favorite programming language, how easy is it for me to implement it? For example, some of the more theoretically best known algorithms sometimes don't really have the best or easiest way of being implemented. Sometimes that's not true. Another one kind of related is difficulty. How about a difficulty to modify or augment? So I give you some algorithm, and okay, well, it works and solves this particular problem. How easy is it to modify the algorithm to solve other problems? Or say, as we're going to see later on in this course, we're going to talk about graphs. A lot of problems on graphs tend to be very easy to modify to create other problems, which create all sorts of intricacies that you have to deal with. Sometimes the algorithms there might be quite easy to augment to allow for very simple behavior changes. And sometimes it works just fine. Sometimes that isn't true. But that's either way a nice characteristic. How about running time? So if I take the algorithm and I implement it on a computer, and I execute it. Probably what would be ideal is if this doesn't take too long to finish. For example, if I give my computer program to somebody to execute, and say time is money for them, it would be a big deal if this thing takes a really long time. They will not like that unless it really measures up for the quality of the answers that they're getting. So this is a big one. Running time. How about this? Well, not necessarily as important as it used to be. It still can be rather important in some settings. Is space or memory usage? So this definitely has its own place and importance. If, say, you create an algorithm and it requires an exponential amount of space, whereas there might be a better algorithm that doesn't necessarily, maybe this was really easy to implement, but it really consumes a lot of memory. You might want to have it where maybe you may be programming a video game or something. You wouldn't want to have it where your user isn't going to be required to have maybe 10 gigs of memory allocated and stored so that they can use and run your game. That's not very ideal. Likewise, if I have an industrial application, if I don't have very heavy-duty computer resources, it could break it. It could be a deal breaker if your program just. If you have a lot of multitasking going on in these machines, you may not necessarily want that kind of characteristic. there was a time where this was much more important, when space wasn't so cheap. But I just want to give you a flavor of the kinds of things that people might think about when it comes to comparing algorithms. So the biggest thing that we're going to talk about in this class is complexity. So you may have seen some of this in a previous course. However, I'm going to go much deeper than you've probably seen in previous courses. So complexity, so this definition of complexity is the amount of computer resources an algorithm uses. So there's going to be two kinds of complexities that we're going to be interested in this course. One more than the other, and I'll give you a very simple explanation why. So the first one is space complexity. So this is the amount of memory the algorithm needs. So just before I get too specific, if I talk about algorithm needs in terms of the space, in this course I'm going to assume that the input is given to you. What I'm going to be referring to as the space complexity is the additional amount of space you use beyond being provided the input. For example, if you have a sorting problem and you sort the entire algorithm, not the algorithm, if you entirely sort the array that you're provided without needing to create a duplicate array or some extra memory, for example, say another array or something. This would be something you count towards the space complexity. I must mention this because there's some other more kind of theoretical edges where space complexity would also include the input being provided. I'll give you a simple justification of why this isn't terribly interesting in an algorithms discussion. It's because if I give you, say, an algorithm for sorting, what would matter is that your algorithm doesn't require extra use of an extra array or additional variables that would maybe create a lot of overhead. However, if I include the input size in that, you can simply say, okay, well, the space complexity is going to be linear in the length of the array at least. But what we would like to do is make careful considerations between if they're having extra space beyond the array being provided, or those that simply they just do everything in place, where I don't require any additional memory beyond maybe some constant number of variables. So that's the convention we're going to use. So the convention I'm using is often called auxiliary space or extra space. So just keep that in mind. So that's what we're going to refer to as space complexity. It's pretty common in algorithms. And time complexity is going to be one that we're going to consider a lot in this class. So it's the amount of time needed by the algorithm to complete its computations. So you might ask, Dan, you alluded that there's like some difference between these two in importance. I should mention something very important and why I'm going to talk about space complexity a bit in this class. However, I'm going to focus mostly on time complexity. It's a very simple explanation. I could reuse space. So when I'm done doing a computation, I could reuse the space for which I'm using, or even during an execution of an algorithm, I could reuse space that I previously occupied at some stage by removing or deallocating memory afterwards. So in practical terms, if I use some space, I can reuse that space when I'm done, right? However, time is not something I can do that with. I don't have a time machine. I can't simply just go back in time because I've still used that time up. So regardless, we're not going to get into too many hypothetical discussions about time machines here. The point is that time, the amount of work I have to do, has to still get done, and it's expended. I could change the traversal for which time is executed. Okay? So the big thing that you want to keep in mind is that the algorithm's complexity is derived as a so-called complexity or growth function. I'll refer to it as usually a complexity function. So we derive it using some type of analysis. So let me define what a complexity function is. Okay, so a complexity function is we're going to call it a function f. A function f on the size of the input. On the size of the input. So remember we talked about this is input size. And we'll say on the size of the input n. which we will often write as f of n as an abbreviation. And it's worth noting that technically this is an abuse of notation. So I'm just going to remark that I'm going to say though f of n is the output of function f given n. We will assume functions on the domain of positive integers to positive real numbers. More formally, I'm saying that function f, it takes positive integers and maps them to positive real numbers. So this is the set of all positive integers. It's indicated with this plus. And this is the set of all positive real numbers. So this black bold R represents real numbers. These are things like your decimals. These are irrational numbers. And the plus indicates that it's positive. Likewise, this is the set of all positive integers. This is a blackboard Z. So just simply, complexity function is just a function defined in this fashion. And note, I will just use a little bit of abusive notation by sometimes describing the function as f of n, even though technically its name is f and its input is n. This is just because I'm using it as a shorthand to make it easier so I don't have to define what the parameter is every single time. It's an abbreviation, a common abusive notation. So to determine the complexity function, we can consider three different analyses. So, just to make this easier, I'm going to draw on a fun analogy. So give me one moment. I got my special little guest here. So this is Lola. So Lola, she is a fun little puppy. Lola, say hi. Hello. And Lola, she really, really likes to eat little things here or there. Now, what we're going to find in our analysis of algorithms, what we're going to find for deriving our complexity function is we want to look out for certain problem instances that cause certain behavior for our algorithm. So little Lola here, she really, really, really likes to eat certain things. Now, sometimes they aren't really good for her. Some things that she thinks are good for her are things like greens. She loves greens. And these are perfectly fine for her. She goes outside, no problem. She doesn't get sick. However, sometimes she likes to be a little bit of a funny puppy, and she likes to go eat poop outside. And sometimes, I don't know if it makes her sick or not. And I want to make sure she doesn't do that, because she's a little dog, right? Likewise, there might be all sorts of different things out there she'd like to eat. Now, some of those things make her sick, and I don't want her to get sick. Likewise, there's things that she eats, they're perfectly fine. However, I want to identify the things that she really likes. They don't make her sick or anything. Then there's things that are out there that she's kind of typically, and they don't make her sick or anything, but sometimes they might. Say if they're not served correctly, like it's like a little bit of chicken or something, it's a little old or something. And then lastly, there's the things she shouldn't be eating, like poop. Lola, do you like eating poop? No. You wouldn't admit that on camera. The point is that she really likes greenies, right? Now, in our analyses, you're going to find that we're going to take different case-based analyses. Just like if you had your favorite pet, you want to look out for your pet to make sure they're not eating anything they're not supposed to and get sick. We don't want our friends to get sick. So you're going to find that there's 3 different kinds of cases which we're going to have to be careful for, okay? Here, Lola, do you want the greenie? Yes, you'll eat it later. Anyways, our little friend here, she went back to go have a nap. So let's get started here. So the first thing you want to consider is different cases. So the first, most obvious one in our analogy would be things that, say, Lola really likes. And they don't do anything bad to her, right? Remember, we want to identify things that Lola likes to eat, but we care more about what it does to her. So we're going to try to avoid those things that make her feel sick. We don't want the diarrhea or the poop or the pukies on the ground in the morning when you wake up. Let's just say I've had too many of those situations once in a blue moon. Okay, so here we go. So the first type of case analysis we're going to consider is so-called best case analysis. So best case analysis. So what we're going to do is we're just going to consider the best case scenario. The best case scenario. So this is the analysis of the algorithm. Using a best problem instance. The best is in quotation marks. A best problem instance. So in terms of the algorithm, the best problem instances are those for which the algorithm terminates earliest. So it takes the minimum number of steps. So just as an example, I'm going to consider each one of these cases linear search. So for example, a best case instance would look like, so a best case instance in linear search, I'll just abbreviate as LS, are those where X, remember X is the key or value we're looking for, is located where? Where is it located? It's located in the first element. The first element considered in L. Now remember, L is just the input array here. How many comparisons does that require? It requires just one, right? Requires one comparison. There, look at you, like that's easy. So that's the best case analysis. Now, oftentimes the best case analysis doesn't give you a whole lot of insight in how the algorithm behaves, but it's something good to know. Sometimes algorithms perform very well sometimes. However, sometimes they perform very poorly. We want something kind of in the middle sometimes. So this brings me to talking about average case analysis. So this is the second of these 3. Remember, this is like if Lola, she likes to eat some things sometimes, or if your favorite pet, she likes to eat some stuff, or he likes to eat some stuff. There's a whole range of things that the dog, or the cat, or whatever pet you might have, or your goldfish, might like to eat. And sometimes it's good for them, sometimes it's blah. It's not that fun. The point is that I want to capture sort of an average or typical case. So this is the point of average case analysis. Or average case analysis. So this, you can think of this as on average. The analysis using all the problem instances when possible, put that in parentheses, when possible, over some probability, I'll abbreviate that as probability distribution. And I should mention that typically this is over a uniform distribution. So what do I mean by uniform distribution? It means that all outcomes are equally likely. So hence why we call average here. So let me do an example with this. So before I can, I need to be a little bit careful here. Okay. This type of analysis requires a little bit of statistics, so I'm going to be very particular about this. So I'm just going to say this analysis requires a bit of statistics. So here's the idea. Compute the average number of steps performed of all possible problem instances over the probability distribution. For each instance is assigned a probability of occurring. Then, now if you know your stats, you might know this, then the goal is to compute the average in parentheses, I'm going to put expected value of some random variable. So what is expected value? Now, you may know what expected value is, but I'm going to anyway define expected value, at least in the way that we're going to need it. I must stress that you're going to find that I'm not going to focus so much on average case, because it typically can be difficult to perform average case analysis all the time. Likewise, we have to be always be careful, because when you're computing the average case, it's not necessarily going to be the case that the that the instances you look at are going to take on the behavior of the average case. It's just, you got to look at it like at random, this is sort of what the algorithm will do. But that doesn't mean it's actually going to do the thing that the average case is going to say. It's just what you would expect it to do. So I'm just going to define expected value, and I'm going to do an example of how you can use it to do average case analysis for linear search. So I'm going to let x be a discrete random variable with finite outcomes, x sub 1, x sub 2, x sub 3, and so on to x sub n, which occur with probabilities p sub 1, p sub 2, until p sub n. So I give you a set of possible outcomes, each with a probability. So what I want to do is I want to compute the average. Imagine, so I plot something into x, what's the average? So I have a bunch of outcomes, each with a probability. I want to compute what the average over x is going to be. So let me just write out that. Now, let's see. Then, let me finish this off. I'm going to use a comment instead of a period. It's a crafty move there. Then, the expectation of x denoted blackboard e of x, like this. This is going to be equal to the sum from I is equal to 1 to n. The upper limit here is n, the lower limit is 1. Well, I is equal to 1. And it's going to be pi times xi. So just be warned. Remember, not every instance will be the expected value. However, I want you to notice something very simple here. And this is what's going to make things a little easier for us to understand. Okay, when all the probabilities, p sub 1, p sub 2, p sub all the way up to p sub n, are all equal to one another, this is just simply the simple average calculation. So it means that all of these p sub i's are going to be all equal to one another. I pull this out in front, and then you realize you're just adding up all these outcome values, and then all I do is I divide it by whatever. So if the probability is 1 over something, it will be the sum of these over that 1 over something, which would in fact be just an average calculation. So just keep that in mind. When all the probabilities are equal, it's just a simple average calculation. When it isn't, it's a weighted average. So don't let this get too complicated. Remember, just think average in our cases, because usually we're assuming a uniform distribution. So for our example, we're going to consider a distribution that looks like this. This is typical. Assume Px is equally likely to occur anywhere in L. Anywhere in L. Now, when I say this, that implicitly means that X is somewhere in L, right? It's equally likely to occur. Now, there are n positions in my array, so what's the probability for which X is going to appear in one of those spots? Well, you have 1, so imagine I just have Px. Now keep in mind that X may appear multiple times in there. So I'm just going to assume that all the entries are distinct, but you'll realize that if I just simply assume that X appears more than once, I'm just actually going to increase the probability it's going to occur. So if I just assume that X and all the other numbers are all distinct, it doesn't really make much of a difference. I just care that x of p is equally likely to occur. So it might be just the case that they're all just distinct and x is just there, but I make the assumption that it's equally likely to occur. I'm just going to be very pessimistic in my analysis. So what's the probability then? So that is the probability it is in some position is some position I, let's be clear, some position I is 1 over n, right? Just like if you thought about rolling a die, there's 6 sides, so if I were to get a chance of rolling it onto the side I want, it's 1 over 6, just 1 over n. It's not too terribly complicated. Now, I want you to observe this. This is very important for what we're going to do. There are instances where x is in the first position. It's in the first position. X is in the second position. X is in the third position. Third position. And so on until x is in the last position. Now, for each one of these respectively, the number of comparisons, to find the first position is 1. Second is 2, and so on. And the number, let me go over here, and the number when in the last position is what? It's n, right? So I'm just counting up the number of comparisons possible. Okay. So if you think about this, what I can do is I can take all my instances that are over this probability distribution. So remember, I'm only considering the ones where x appears in the array. So all I have to do, and also one thing worth noting is that we only care about where it just appears, because remember, if there were more than one, I wouldn't really care, because I'll just find the first spot it appears, right? That's how linear search works. But the point is that there are instances where x is in the first position, so there's going to be a whole bunch of instances where the first position has x, a bunch with the second position, some with the third, some with the fourth, and so on until the last position. So I can take all my instances that are over this distribution, split them up into pieces. So I have n sets of instances, and now all I have to do is look at them. Okay, well, they're all equally likely, right? So that might be easy enough to imagine that, okay, well, the probability here was 1 over n, so all I have to do is just sum up the number of comparisons that happen over them over n, right? Because there's n sets of instances, each one with a certain number of comparisons. I add up all of those, and that's one way you can get the average case. I'm going to show you how you can calculate it out more formally. just because I brought up expected value, so I'm going to show you how you can use it. Let x be a random variable that is the number of comparisons. The number of comparisons. So that x sub 1 is equal to 1, x sub 2 is equal to 2, and so on until we get to x sub n is equal to n. And pi is the probability that the algorithm performs I comparisons. So that being said, so remember, each of these are my possible outcomes. Just like I said, there's going to be n possible outcomes here. So I've just assigned each one the count of how many there could be possible, and I'm just going to take an average over all of them, right? So I'm just going to invoke this definition by observing that, okay, well, the probability of each one of these is 1 over n, right? That's what we established earlier. So, well, pi is equal to 1 over n, so the average number of comparisons in linear search is the expected value of x, which I'm just going to invoke the definition. Remember, we always go to the definition. This is the definition here. So I'm just going to plop that in, and then I'm just going to massage it a bit. So I go I 1 to n. Now remember, this is sigma notation. So if you were to expand this out, it would be p sub 1 times x sub 1 plus p sub 2 times x sub 2 plus p sub 3 times x sub 3, and so on all the way up to p sub n times x sub n. So pi xi. Well, what is this? P sub I, remember we established is 1 over n, right? Now here's the great part. Each one of these xi's matches exactly, so if I give you x sub I, it's just equal to I, right? So I could just plop that in, right? It's not too hard. So I got 1 over n times I. Well, what is that? Well, each time I'm adding, I multiply by 1 over n. What I could do is, if you list them out all together, I can actually factor out 1 over n, and I can do the following. So I have 1 over n times the sum from I is equal to 1 to n of I. Now, you might ask, okay, well, Dan, what do I do with this sigma? Well, how do I do with the summation here? So, what do I do with this? Well, notice that this actually has a particular so-called closed form. So what do I mean by that? There's actually a formula that actually you can evaluate that's very simple that actually sums up all of these numbers. So this is 1 plus 2 plus 3 plus 4 plus 5 and so on. Well, this actually has a nice closed form. This is called the arithmetic series, right? So this is just the arithmetic. It's worth noting that I will give you a whole list of these different closed forms. We'll invoke some of these during the term, so just keep that in mind. I won't expect you to memorize these. Like, okay, this one's I will expect you to know this particular one, but the other ones, maybe not so much. Regardless, I like to usually give you a list of all the closed forms whenever I can. At least in this course. It might be different in an upper year class. So, this has a well-known closed form. It's n times n plus 1 over 2. So it's the upper limit times the upper limit plus 1 all over 2. So it's 1 over n times n plus 1 all over 2. So I have 1 over n times n plus 1 over 2. Well, here's the great thing. There's 1 over n there, and there's an n there, so those two will cancel each other out nicely, because it just becomes 1 there. And I end up with just n plus 1 over 2. So what do I mean by this? So that means that on average, you should expect the algorithm to perform n plus 1 over 2, so roughly half of the array should be looked at in linear sequence, which should be what you would expect if I averaged over all of the number of comparisons, right? It should be somewhere about the middle. So that's an example of average case analysis. You'll find that I won't be doing a whole lot of average case analysis because, as you can see, you have to be very careful. Likewise, it's interesting, but it's not particularly easy unless you're really, really good at stats. Likewise, you also have to have a lot of information about the distribution. So sometimes it just makes it very difficult. And likewise, there are limitations, right? I picked a distribution for which I knew that the key existed. There's actually a different calculation you have to do if you wanted to, say, consider when x isn't in the array. Okay, now I want to focus on the last of these 3, and this one is the one that you'll find that I will focus on in this course. Where did, oh, there it is. Excellent. So this brings me to worst case analysis. Worst case analysis. So remember I had my cute little puppy dog Lola? If she eats some poop outside or eats a little bit of some bad food, that she might get some really bad diarrhea or barf from the floor. We don't want that to happen, but I need to be aware of it so I can prevent it from happening. Or to better understand Lola's eating behavior, okay? You gotta look at algorithms almost like animals that are trying to do some activity. Best case, that's like where they're not going to do any harm to anybody or they aren't going to hurt themselves or something. Average is where you kind of look at, on average, it's going to do this. In the worst case, this is the stuff that we don't want to happen to the cute little puppy named Lola. Okay, so this is where we're going to analyze the worst case scenario. So this is me just using, so this is the analysis using worst problem instances. So back to my analogy, this would be the equivalent of we're eating some bad chicken or eating poop outside. I want to identify these problem instances so I have a better understanding of what bad things could happen if say, the puppy or your favorite animal ate them. So I have a better understanding of these situations because we're going to be pessimistic when we analyze algorithms. We're going to think of the worst possible situation that possibly could occur with our algorithm, so we have a better understanding how bad it could get. So the point is not to hurt the puppy. We're trying to understand what the puppy wants to eat so we can make sure we don't let the puppy have those things. Likewise, it helps us also address those situations, right? You're going to see that oftentimes worst case scenarios help us better design the algorithms. So sometimes there's some problem with some algorithm. We want to oftentimes address that problem, and oftentimes we come up with a better algorithm sometimes. Okay. So I just want to mention that if we have the worst case time complexity of an algorithm, this is the most important thing you should know about this, then we know the algorithm will never, and I really mean never, will never run longer than the running time specified specified by this analysis. So just think of the worst possible scenario that can happen when it comes to your algorithm. So in the case of linear search, so if I'm thinking linear search, a natural one is when X is not in L. How many comparisons does that mean? Okay, well I have to scan from left to right. So I go, oh, boom, 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 through each one of the positions. I don't find it, right? Well, how many comparisons did I have to do? N, right? So I require, so requires N comparisons. So what you want to do is you want to identify the instances for which the algorithm is going to do its worst. So there's going to be a whole set of instances, these worst problem instances, that do this. And we can't do any worse than that, because I check every element in the array. And that's what linear search does. Okay. So the focus in this class, I should stress, is worst case analysis. Because oftentimes we're interested in how much resources we're going to need to solve certain problems. It's not on average is how many resources we're going to need. We're going to need how much we're going to need, right? That's kind of the plan here. So I want to talk a little bit about a couple quick things before we finish for today. So when I talk about time, I keep talking about time. Like, what do I mean by time? So we need some clock, right? Because we need to measure time. So we need some sort of clock to measure time. And a machine, I'll put in quotation marks, for our analysis. Because we want to do it in a way such that we don't expose any holes in our analysis. So just because I need to make sure I present a broad set of views to you, I want to talk about the idea that you could experimentally analyze the algorithm. So experimental. So here's an experimental way of approaching this. But what would you need if you're doing an experiment? You're probably going to need a computer, right? So your like laptop or, I don't know, your cat? I don't know, some computer. I'm just joking, of course. Don't use your cat as a calculator, okay? They don't like that. Okay. We're going to need an operating system to run the program on our computer. We're going to obviously need a compiler for the programming language. The algorithm is implemented in. So we need some compiler so I can actually like write up my favorite algorithm in a programming language so I can compile it, so I can execute it as machine code. So these are things I'm going to need probably. But I should point out a few drawbacks of this approach, but you don't necessarily have to look at them as drawbacks, you have to just be nuanced about this. So you might be considering saying, okay, well that seems time consuming and expensive. Because remember, if you want to do a very good computer experiment, you must be thorough. Otherwise we might be, like I said, we could potentially be misleading somebody. Like, heck, we could be even lying to ourselves. The reason why I bring this up is that we must consider all problem instances, right? We usually can't do this. right? Because remember, I have an infinite collection of problem instances. There ain't going to be a way I'm going to be able to run each one of those on my computer without an infinite amount of time, right? At least in most circumstances. So results depend on the input selected. So I pick particular inputs when I do my experiment. You want to try to find ones that seem reasonable. So a uniform distribution, overall a bunch of instances, maybe might be reasonable if you're interested about practical usefulness of an algorithm, possibly. However, you might also be interested in really tough instances. So you might develop something like a benchmark for which you find really tough instances that maybe have some theoretical interest attached to them. That might be another way you can approach things experimentally. The key thing is that you have to be very clear of how you did it and the method for which you required those. So the biggest drawback that you have to be very careful of when it comes to this approach is results depend on a particular implementation. So when I say implementation, I mean like your computer itself. Like on the computer, you wrote up a program. Particular implementation and the machine it was timed on. So I mean, I start up my stopwatch, I determine how long the execution takes, that's what I mean. So a lot of programming languages, you just use some of their timing functions to calculate how long the program executes. But this is the big point I want to make, and this is going to be the point I'll leave off on this lecture, is this one. This is the big one. As a result of this. We don't want our results to just depend on one particular computer, right? We want them to be true regardless of which computer I put it on. This approach is machine dependent. It's machine dependent. So when I write it up on my laptop and I run it on my laptop, it depends on the results depend on that machine. So if I have two machines, I would have to make sure that their specs roughly line up, or almost exactly line up if I want to be very formal. That is a big drawback. So I want you to just be aware of these limitations. So if you're doing an experiment, just be aware of these limitations. Should you use a computer experiment? Not to say computer experiments are bad or anything. Just these are drawbacks you need to consider involving an experimental approach. One of the more traditional computer science approaches is not to make it about the machine you're implementing it on. You want to make it machine independent. So we'll talk about that more next time, okay? So that being said, we're going to stop right here. Have yourself a beautiful day.